Good morning, students. Real nature of radiation and matter. In that we are following the video 2 or lecture 2. According to deleted syllabus model papers. From this chapter already we have discussed that 6 marks weightage. In that 2 model papers what they gave? That are 1 numerical and 1 mark questions. The 2 model papers contains only numerical and 1 mark questions. So according to that first video we discussed that 1 mark questions except that experiment. Remaining all points are nothing but 1 mark questions only. So here also we are discussing 1 mark questions. What are that? First one is, how does the stopping potential of photosensitive material vary with intensity of incident radiation? In yesterday's video already we discussed what is the stopping potential, at which negative potential the photocurrent will be 0. That negative potential is called stopping potential. We have discussed that point already. So according to that, the intensity of incident radiation does not depend upon for this stopping potential. How much intensity you can take, up to certain it will be increased, then after it will saturate. Okay, the graph will be comes like this. This is the stopping potential V0. So if you take any one material, that it will increases with the potential, and at a particular stage it will be saturated. This is the intensity of incident radiation. How much you increase that? Clear na? Intensity, how much you increase that, for that material stopping potential does not change. Clear? The graph will be like that. Next one is, what are matter waves? Very, very important question. What are matter waves or de Broglie waves? Because of de Broglie measured this one, invented this one. So, what are matter waves? Very, very simple. What is that? The waves associated with moving material particles. The waves associated with moving material particles are known as matter waves. Elementary particles, what it releases the waves. Elementary particles means already we know, basically we have 3 that are electrons, proton, okay, neutrons, like that. But we have not that 3, so many we have. Up to 15 we have elementary particles in our nature. But here de Broglie consider that elementary particles, the elementary particles which release the waves while they are moving, that are called de Broglie waves or matter waves. De Broglie waves are matter waves. Very, very simple definition it is. The waves associated with moving material particle. The waves associated with moving material particle, that are called matter waves. Most important. That matter waves releases a wavelength. That are, what is, or write the equation for de Broglie wavelength. Write the equations for de Broglie wavelength. It represents with lambda. How can you write? Very, very simple equation. Lambda equal to h by p or h by mv. Here p is nothing but momentum of the moving material particle, or simply particle. Momentum of the particle. What is that momentum? Mass into velocity, or it represents with p. P equal to mv, already we knows that. Everyone knows that p equal to mv. Clear? So now lambda equal to h by p or h by mv, where mv is momentum of the charged particle. Momentum of the elementary particle. Here, according to the charge, how the de Broglie wavelength will vary with applied accelerating potential. If applied accelerating potential increases, what happens? Lambda value will decreases. That only the relation here. What is that? See that how does the de Broglie wavelength of a charged particle change with accelerating potential? The de Broglie wavelength of charged particle decreases. Lambda decreases for the charged particle when? With increasing potential. With increase in accelerating potential. Are you understand? Very simple. Lambda value decreases with increase in accelerating potential. Increase in accelerating potential. Very simple question. Clear na? Lambda of charged particle R decreases with increase in accelerating potential. Clear na? That is one more question. Next one is, how does the de Broglie wavelength can vary? R, which has the smaller wavelength for proton and electron. Here we have the charged particles are there. Okay, the charged particles are proton and electron. They have same kinetic energy. Here condition one more they gave. If it is the same momentum means lambda value will be remains change with the accelerating potential. Now here what they gave, proton and electron have same kinetic energy. Kinetic energy will be same, work done will be same for that. Kinetic energy will be same for these proton and electron, which have smaller de Broglie wavelength. Here already we know that lambda equal to h by mv. In this one, mass of proton is more compared with electron. Mass of proton is more compared with electron. If more, which have more mass, they have less wavelength. According to this relation, inversely ratio, simply one more word, inversely. So which have less de Broglie wavelength, smaller de Broglie wavelength, for proton is a smaller wavelength. Clear? Next one is, in previous 12th and 13th questions, what we are discussing, that is here once again with respect to one formula we are discussing. What is that here? Write the expression for de Broglie wavelength in terms of, for a charged particle, in terms of accelerating potential. So what you can write? Lambda equal to de Broglie wavelength, already we know that h by p or h by mv. What about momentum and kinetic energy relation? Are you know? The kinetic energy K equal to, previous already we wrote K equal to P square by 2m. Says or no? In this one, kinetic energy is here by applying the potential, accelerating potential. So what we will write, respect of that, we will write VQ. Because of energy or work done will be same. So work done W equal to what you can write, VQ. Clear? That's why respect of work done only I told previous. Okay. Now VQ equal to what you can write, P square by 2m. Clear? This 2m will come to this side, then P equal to under root 2m QV. Clear na? So respect of here momentum P, that what we will write under root h by under root 2m VQ or QV. Here in this one, previous what we are discussing, the 12th and 13th questions. So here proton and electron which have more. Okay, how does it will be varied with accelerating potential? That lambda will be smaller for proton. Already we discussed that. Why? Because here in this relation, charge of proton and electrons be same. V must be kept, accelerating potential must be kept constant, so that what it happens, mass of the proton is more. So according to this relation, lambda proportional to 1 by root m, or simply we will call lambda inversely proportional to square root of mass. Inversely proportional to square root of mass. Okay. So what we will write here, lambda inversely proportional to root of 1 by root of m. Clear? Clear na? So that mass of proton is more. So what happened? For proton, de Broglie wavelength is small. Similarly, if here these are all kept constant, then lambda inversely proportional to root v. Same. So that's why if you decrease here, if you want to be increase the accelerating potential, if it is increased, lambda value will decrease. That is the 12th question and this is the 13th question. Clear na? For that explanation only we are giving here one equation, that is lambda equal to h by under root 2 mqv. Suppose for electron, if they will ask lambda, how to write lambda equal to h by, instead of this charged particle, here charge is nothing but electron charge. So what we will write, instead of q we will write e. For proton and electron both the charge will be remains the same, only magnitude of charge will be remains same. So we will write for this one, for both the electron and proton. Clear? This is the most important equation. Write the expression for de Broglie wavelength with accelerating potential lambda equal to h by mvr. Here v is nothing but velocity here. Don't get confused. Here momentum. In this momentum v is nothing but velocity only. Here it is a capital V. Capital V means accelerating potential. Don't get confused this one. Okay. So lambda equal to h by under root 2m under root 2m qb. Clear? Here state Heisenberg uncertainty principle. Anyone can know, this is already learned in chemistry. So here and there both are same. At a time, at a particular same instant of time, both momentum and position we cannot measure. Okay. At a particular instant of time, both we cannot be measured. It is impossible to measure both position and momentum. Both position and momentum. Clear na? So here that statement given. What is that? It is not possible to measure both position and momentum. Position means nothing but delta x uncertainty position, where here one formula is given, delta x delta v equal to h by 2 pi. Say yes or no? So here delta x is nothing but uncertainty position of particle. Okay, delta v is uncertainty change in momentum. Both we cannot be measured. It is not possible at a time. Clear? That is called Heisenberg uncertainty principle. Most important. Delta x into delta v equal to h by 2 pi. Okay, these are all theory concepts. Now we are discussing numericals. In numericals, it is reduced syllabus new model papers given by the board. In that numericals only first we are discussing, then after reminding. Okay. In that first one is, first numerical is the work function of cesium material is given. Work function they gave. Work function means it is nothing but a phi naught. Okay. So phi naught already we know that. So phi naught from work function. What you can write the equation, work function phi naught equal to h nu naught, Planck's constant into threshold frequency. Okay, so that is given. How much it is? 2.14 eV, electron volt. Okay, in that first what they are asking, find the threshold frequency. So by using this work function equation, if you will measure nu naught, then we can, first point will be over, finished. Next one is the wavelength of incident light if the photocurrent brought to zero by a stopping potential. Because of definition of stopping potential is that only, previous I told, at which negative potential the photocurrent will be become zero. Clear? So that only they give. Photocurrent brought to zero, that is nothing but a stopping potential. The stopping potential, how much they gave? 0.6. By using this data, they are asking wavelength. Second point is wavelength. So first point we want to measure here, that is a point to measure. First here what it is? Threshold. Threshold, threshold frequency. To measure that we are using work function equation. Work function phi naught equal to h nu naught. Work function already we measured here one value, that is 2.14 into 1.6 into 10 power minus 19. Why? Because here EV 1 electron volt equal to 1.6 into 10 power minus 19 joule. Clear na? So in terms of EV, what I substitute here 1.6 into 10 power minus 19. So this is a phi naught value, that equal to h. Here in this numerical h value not given, so we need to be remember, that is Planck's constant h equals to 6.63 into 10 power minus 34 joule second. Okay, so instead of this h, what can I write? 6.63 into 10 power minus 34 into nu naught. By using this one nu naught equation, nu naught equal to 2.14 into 10 1.6 into 10 power minus 19 by 6.63 into 10 power minus 34. If you will cancel these all, how much you get? 5 point. You can get 5 point. Okay. 5.164, 5.164. Numerically, if you be multiply and if you be divide this one, you can get that 5.164 into here 34 will move up. Then how much you get? 10 power. Finally it will get 10 power 11 H. This is the threshold frequency nu naught equal to 5.164 into 10 power 11 H. This is the first point answer, A point answer. Next point is B point. What is again the B point? That B point to measure that, first we want to measure total energy. In energy of total incident ray. So total energy E equal to what you can write? Work function plus kinetic energy maximum. Why? Because according to Einstein's equation, what you can write? Phi naught plus Ke max. This kinetic energy maximum, how can you write? E equal to phi naught plus EV naught in terms of stopping potential. In terms of stopping potential, what you can write? EV naught. Okay. Then already phi naught value here in terms of electron volt, and similarly stopping potential is also we knows that. So what we can write? E equal to phi naught value 2.14 EV plus electron volt. So E into what about the stopping potential? It is nothing but 0.6 V. So this E, if you take this side, 1 electron volt it is. Okay, so E is nothing but 1.6 into 10 power minus 19. So here EV here also be same na. So we will add these two. So total energy E equal to what you can add? If you want to be add for this one 0.6, then how much you get? Here 0.60. If we can write like this, then how much it is? It will be become as 2.74 electron volt. So 1 electron volt, how much you write? 2.74 into 1.6 into 10 power minus 19 joules. Okay. So 2.74 into 1.6 into 10 power minus 19. This is the total energy. Now energy E equal to what you can write according to that? Hc by lambda, or simply Hc we can write energy equal to H nu. Nu is nothing but C by lambda. Okay. So I want to write Hc by lambda directly. From this one, lambda equal to what can I write? Hc by energy E. What about H value? Here already we know that. So lambda equal to H value, how much it is? 6.63 into 10 power minus 34 into what about light velocity? It is nothing but 3 into 10 power 8. Already we know that. So 3 into 10 power 8 by energy already here we measured. How much it is? 2.74 into 1.6 into 10 power minus 19. If you want to be substitute these all values, and you can get one final value, that is how much it is? 4536 into 10 power minus 10 meter. 10 power minus 10 means angstrom. So final answer lambda equal to 4536 angstrom it will come. Okay. This is the first numerical which is given in a reduced model paper. Reduced syllabus model paper. Second numerical is the light frequency. Frequency means what they gave? Nu. The light frequency given. So that is 7.21 into 10 power 14 H. Okay. Is incident on metal surface. The cutoff wavelength for photoelectric emission. Cutoff wavelength for photoelectric emission means nothing but lambda max. Threshold wavelength. Okay. That is called lambda naught we wrote. Threshold wavelength. Okay. So cutoff wavelength or threshold wavelength, how much they gave? 540 nanometer. By using this data, what they are asking? Determine the kinetic energy, simply determine the speed of electron emitted by the metal surface. Photoelectrons. Speed of the photoelectrons which are emitted from the metal surface. They are asking that speed. So, to know that, we want to be find out first Einstein's photoelectric equation. What it is? Very simple. Already we wrote energy E equal to what we will write? Some energy will utilize to do work function and remaining will be kinetic energy maximum. Remaining energy will get to released with the kinetic energy maximum to the speed of electrons, photoelectrons. So from that speed they are asking. So what you can write? K max equal to what you can write? So this phi naught take this side, then E minus phi naught. So to substitute this in this equation, first we want to be measure phi naught. How to measure the phi naught? Already lambda value we know that. So phi naught means work done, work function. So here I am writing about that work function. What is the work function? It represents with the phi naught. Phi naught equal to H nu naught. So nu naught, how you write in terms of lambda? So I will write as H into C by lambda. What I wrote? Nu equal to C by lambda. Already everyone knows that. So here lambda nu naught. So here in terms of lambda naught, how you write? C by lambda naught. So HC by lambda naught. That equation will be nothing but phi naught equal to HC by lambda naught. Okay. So by using this one, what can I write now? Phi naught equal to HC by lambda naught. So phi naught equal to H value already we know that 6.63 into 10 power minus 34. Already in this numerical only they gave. If not, we must be rememberable that value. Okay, 6.63 into 10 power minus 34 joule second. And C value already we know that 3 into 10 power 8 meter per second. By lambda naught how much they gave? 540 into 10 power minus 9 meter. Nanometers they gave. Nano means how much it is? 10 power minus 9. So 540 into 10 power minus 9 I wrote. By using this one, after calculation, how much you get the value? Phi naught equal to 3 points. Phi naught equal to, if we cancel these all, finally you can get the value of 3.683. 3.683 into 10 power minus 19 joule. It will come out. Okay. This is the phi naught value to substitute in this equation. Suppose if you feel it is as equation number 1, then you can write it is equation number 2 to substitute the values. Okay. Then after E you can measure. How you measure the E? Energy of that photoelectrons or incident radiation. Okay. Incident radiation of energy. How can you write? E equal to H nu. E equal to H nu. Already nu value given. How much its frequency? 7.21 into 10 power 14. H value also we know that. So from that E equal to what you can write 6.63 into 10 power minus 34 into new value 7.21 into 10 power 14 H. Okay, if you will multiply these two, how much you get? You can get the value of 4.78. Okay, total energy E equal to 4.78 into 10 power minus 19 joule. You can get this value. This is equation number 3. Okay, now these two are substituted here. So kinetic energy maximum means what you can write half m V max square, that equal to E value how much it is? E value how much it is? How much you measured? 4.78 into 10 power minus 19 minus phi naught. Phi naught value how much you measured? 3.683 into 10 power minus 19. Now both you can subtract each other. Okay, then mass of electron here already they gave. So half into mass of electron how much it is? 9.1 into 10 power minus 31 kg. Okay, into V square maximum, that equal to, here after subtraction what you can get that? You can get that the value is, okay, 1.1 into, if you be subtract this one, 1.1 into 10 power minus 19 joule. Okay, from that to take this side and V max square equal to, we want to measure this velocity only. So V max square equal to take that side. So 2 into 1.1 into 10 power minus 19 by, how much it is of mass? 9.1 into 10 power minus 31. If you measure these all after substitutions, okay, so V max equal to under root, if you be substitute these values, 2 into 1.1, that is 2.2 by 9.1, if you be substitute these all, what you can get? You can get 24 into 10 power 10. Under root 24 into 10 power 10. That is nothing but 4. Okay, that is nothing but 25. If it is 5, it will come out. Okay, root 10 power 10 means 10 power 5 it will come. So approximate value 4.89 into 10 power 5 meter per second. This is the velocity of emitted photoelectron. This is the velocity of emitted photoelectron. If you want to write approximate, it is 4.9 or approximate 5. 5 into 10 power 5 meter per second. If you can write approximate calculation. Okay, this is the actual calculation. You can write also with approximate calculations. This is the second sum, which is given in a reduced model, reduced syllabus, the model paper 2. Okay. Another numerical is threshold wavelength of photo. Threshold wavelength means what they give? It is nothing but a lambda naught. So threshold wavelength lambda naught is equals to how much they give? 5000 angstrom. 5000 angstrom. That is nothing but 5000 into 1 angstrom is nothing but 10 power minus 10 meter. Says or no? So that what we will write? 5000 into 10 power minus 10 meter. Clear? Now find the velocity of photoelectrons emitted by it when the intensity of wavelength, intensity of incident radiation of wavelength, what they gave? 4000 angstrom. So lambda value given. So what you can write? Lambda equal to 4000 angstrom. That means 4000 into 10 power minus 10 meter. Okay. Now, Einstein's photoelectric equation, by using that we know that E equal to phi naught plus kinetic energy maximum. So, in terms of lambda, what you can write? hc by lambda, that equal to work function hc by lambda naught. Or simply we will write h nu equal to the same equation, one more words we will write as h nu naught plus k maximum, k max. Okay. because of nu is nothing but a c by lambda, so I wrote hc by lambda that equal to hc by lambda naught plus kinetic energy maximum. By using this K maximum equal to what can I write? hc by lambda minus hc by lambda naught. So h value already we know that, so hc take out common and h value substitute that 6.63 into 10 power minus 34 into light velocity 3 into 10 power 8 into 1 by lambda value how much it is? Nothing but 4000 angstrom, so 4000 into 10 power minus 10 minus 1 by 5000 into 10 power minus 10. If you will solve these all, then what you get? You can get the value of kinetic energy maximum, K maximum equal to how much it is? 10 power minus 19 joule. How much you get? Kinetic energy equals to 10 power minus 19 joule. Already we know that kinetic energy. By using this kinetic energy, we can measure the velocity. How you measure kinetic energy? K maximum equal to what is the formula for that? Kinetic energy K equal to what you can write? Half m into v square max, maximum velocity. So now we want to measure this one. Kinetic energy maximum, how much you have? 10 power minus 19, that is equal to half into mass of electron. How much they gave? 9.1 into 10 power minus 31 into v square maximum. By using this one, I want to write one equation, v square max, that is equal to this 2 take this side, so 2 into 10 power minus 19 by 9.1 into 10 power minus 31. If you be substitute these all values, then finally what you can get? You can get the value of 0.V max equal to 0.22 under root, okay? 0.22 into 10 power 6, you can get that. Inside the root it is 10 power 12 you can get. So V max equal to, if we measure this root, you can get that the value of 0.46 into 10 power 6 meter per second. Okay, this is the maximum velocity. Okay, what you can measure here in this numerical. Okay, like this models and numericals they will ask. All the best. Write well that exam. Okay, prepare well. If you follow these 1 mark and that each and every 1 mark question in this lesson and numericals you can solve well, then you can get the full marks from this lesson. Thank you. All the best.